I want you to picture a scenario. It's practically a rite of passage for anyone living in a northern climate.
Hmm.
It's the dead of winter, the wind is howling, it's minus 30 degrees outside. You shuffle into your kitchen half awake, turn the faucet to get some water for your coffee, and nothing.
Oh, that sound, just a dry, hollow rattle.
Yes, the sound of a homeowner's worst nightmare.
Absolutely.
Exactly. Your pipes are frozen, it's annoying, it's messy, and it is expensive. But now I want you to take that mental image and scale it up. Way, way up.
Hmm.
Imagine you aren't dealing with a half-inch copper pipe under a sink, but a maze of steel arteries in a chemical refinery, or a massive oil pipeline stretching across the frozen tundra.
The stakes change completely at that scale. You aren't just looking at a water bill or, a wet basement. You're looking at catastrophic equipment failure.
Right.
If a pipe carrying hazardous chemicals freezes, it doesn't just stop flowing, it can burst. So
Right.
you're talking millions of dollars in halted production, environmental disasters, serious safety risks.
So today, we are doing a deep dive into the hidden technology that stops that from happening. We're talking about heat trace.
Yeah.
And before you tune out thinking, oh, isn't that just wrapping a heated blanket around a pipe? Let me stop you. The source material we're working with today, it's a stack of technical training modules for industrial electricians.
From places like AIT and AIT, right?
Exactly. And it reveals a world that is just so much more sophisticated than a heated blanket.
It really is. It's a precise electrical ecosystem. I mean, we aren't just trying to keep water from turning to ice. Sometimes we're trying to keep a viscous fluid at exactly 500 degrees Celsius so it flows like liquid instead of, turning into tar,
So it's process control.
as much as it is freeze protection.
Yeah, we're going to decode the 4 distinct architectures of heat trace, from simple wires to some pretty mind-bending physics involving high voltage and magnetic fields. We'll look at how these systems think, how they're installed to defeat heat sinks, and the specific ways electricians have to troubleshoot them when they're buried under 3 inches of insulation.
It's a great example of how engineering solves the same problem, make this pipe hot, in 4 completely different ways, all depending on the need.
So let's get into the hardware. The source material outlines 4 main types of heat trace cable, and they seem to evolve from, let's say, brute force to high-tech.
A good way to put it.
We start with the most fundamental type, series fixed resistance.
This is the classic approach. If you remember your high school physics, this is basically Ohm's law in action.
Okay,
You have a resistor, the wire itself, connected in a simple series loop to a voltage source. Current flows, the wire resists that flow, and that friction creates heat.
it's basically the inside of a toaster, just, stretched out over 100 feet.
In principle, yes. But you can't just run toaster wire through a refinery. In the industrial world, this usually takes the form of mineral insulated cable, or MI cable.
The notes describe MI cable as the tank of the heat trace world. It seems incredibly heavy-duty.
That's a fair description. Picture a copper or maybe a stainless steel tube. Inside that tube, you have your conductor wires, but they aren't just floating in there.
Right.
The space between the wire and the metal tube is packed incredibly tight with a mineral insulation, usually magnesium oxide.
Why the Minvretto packing? Why not just rubber or plastic like a normal extension cord?
Durability and heat. Magnesium oxide is basically rock. It can handle extreme temperatures, heavy impact. If you run over a plastic cable with a forklift, it's toast. If you run over MI cable, you might dent it, but it'll probably keep working. It's designed for the harshest environments you can imagine.
But there's a trade-off.
Yeah.
The notes really emphasize that this stuff is a nightmare to work with if you aren't prepared. It's not exactly user-friendly.
No, it is rigid. And because it's a series circuit one continuous loop, you cannot cut it. That's the big limitation.
Wait. So if I order 100 feet of cable,
Yep.
and I get to the job site, and the pipe is only 95 feet,
You have a big problem. You can't just snip off the extra 5 feet. If you cut it, you break the circuit.
open loop, no heat.
Exactly. Or if you try to shorten it and reconnect it, you change the resistance of the whole system. Less wire means less resistance, which means higher current. You could burn out the cable or trip the breaker.
So it's like a custom-tailored suit. It fits perfectly or it doesn't fit at all.
Exactly right. It's a measure twice, cut once scenario, except you don't even get to cut. It's all factory fabricated to specific lengths.
That seems incredibly restrictive for a construction site where,
Right.
things change constantly. Which I guess brings us to the second type. This one seems designed specifically to solve that flexibility problem. parallel fixed resistance.
Right. This is for when you need that off-the-rack convenience. The best way to visualize this is to imagine a ladder.
A ladder. Okay, with you so far.
You have two long wires running down the sides. Those are the rails of the ladder. Those are your bus conductors carrying the main power.
Got it.
Then the rungs of the ladder are the actual heating elements connecting those two rails.
Ah, I see where this is going. If I chop off the bottom 3 feet of a ladder,
You still have a ladder. You've just removed the last few rungs. The rest of the rungs are still connected to the side rails, still receiving power, and that's the genius of the parallel system.
so you can just...
You can bring a giant spool of this cable to a job site, pull it off the truck, run it along the pipe, and cut it exactly where you need to.
That must be a complete game changer for electricians. You aren't waiting on some custom order from a factory.
Oh, a huge game changer. It speeds up installation massively. But notice the name again. Parallel. Fixed resistance.
Fixed being the operative word there.
Correct. Just like the MI cable, this puts out a constant wattage. If you turn it on, it gets hot. It doesn't care if it's minus 40 or plus 40 outside. It pumps out the same amount of heat.
Which sounds, well, inefficient. If the sun comes out and warms the pipe, the cable is still blasting away. You're wasting energy and potentially overheating whatever's in the pipe.
Exactly. And overheating is a real risk. If you wrap these fixed cables over themselves, like at a valve or a corner, they can create a hot spot.
Because it's double the heat.
Double the heat. And it can burn out the cable or damage the pipe coating.
Okay, so we need something smarter, and this is where the source material gets really, really interesting. The third type, self-regulating cable. The notes call it SMART, but there's no computer chip inside, is there?
No chips, no sensors, no Wi-Fi. It's purely material science. And this is probably the most common type used today just because of how clever it is.
So walk us through the mechanism. How does a piece of plastic know how cold it is?
Well, in these cables, you still have two bus wires, like the ladder, but between them is a special carbon-impregnated polymer.
So plastic mixed with carbon dust.
Essentially, yeah. Now, think about what happens to most materials when they get cold.
They shrink, contract.
They contract. When this polymer gets cold, it contracts on a microscopic level. This forces all those little carbon particles closer together.
And carbon conducts electricity, so if they are squished together,
You create more electrical paths between the bus wires. It's like building more bridges. Lower resistance, higher current, more heat. The colder it gets, the harder it works.
and conversely, when it warms up,
The polymer expands, it stretches on a molecular level, pulling those carbon particles apart. It breaks the electrical paths, so the resistance goes up, current drops, and the heat output just fades away.
that is fascinating. It's effectively an infinite number of microscopic thermostats along every single inch of the cable.
That's the perfect way to visualize it. You could have one end of the cable on a freezing valve getting super hot, and the other end on a warm section of pipe 10 feet away doing almost nothing. It regulates itself inch by inch.
And because it throttles itself down, does that solve the overlapping problem we had with the fixed cable?
Yes, 100%. If you cross this cable over itself, the spot where they cross gets warm. Because it gets warm, the polymer expands and stops producing heat right at that specific spot. It's inherently safe against overheating.
The workhorse.
It's the workhorse of the industry for exactly that reason.
So we have the rugged tank, that's MI, the flexible ladder, the parallel, and the intelligent plastic, self-regulating. But there was a fourth one in the documentation, the heavy hitter.
Yes, the skin effect system.
And this is for...
This is for the long haul.
Hmm.
We're talking pipelines that run for 5, 10, maybe 15 kilometers.
You can't run a standard extension cord 15 kilometers.
Yeah.
I mean, the voltage drop would be massive.
You'd have nothing left at the end. So engineers use something called skin effect. This relies on some complex AC physics that usually bothers electricians, but here we actually harness it.
Okay, explain the setup. It involves a tube welded to the pipe.
Yes. You take a ferromagnetic tube, usually just carbon steel, and you weld it right to the pipe you want to heat. Then you run an insulated conductor wire inside that tube.
Okay, with you.
You connect the wire to the tube at the far end, creating a loop. But because of the magnetic properties of the steel tube and the alternating current, the return current doesn't flow through the whole thickness of the tube. It gets pushed to the edges.
This is the skin effect.
Right. The physics forces the current to hug the inner skin of that steel tube. That concentration of current generates a ton of heat in the tube itself.
But here's the part that blew my mind in the reading. You have this massive current generating heat on the inside of the tube, What's happening on the outside?
Absolutely nothing. Zero voltage.
How is that even possible? We're talking about high voltage here.
Oh, yeah, up to 5,000 volts. But it's because of the skin depth phenomenon in ferromagnetic materials. The magnetic field effectively cancels out the voltage on the outer surface.
Wow.
So you can have a system running at 5,000 volts, which is lethal, generating massive heat inside this little tube, but the outside of the tube is grounded and perfectly safe to touch.
That sounds like magic. A hidden river of fire inside a steel shell, and you can put your hand on it.
It's brilliant physics. It allows us to heat massive lengths of pipeline with a single power source safely and efficiently.
Okay, so those are our 4 players. But having a heater is one thing. Controlling it is something else. We touched on this with the self-regulating cable, but for the fixed resistance types, you can't just plug them in and walk away.
No, you boil the fluid or melt the pipe. You need controls. Historically, this was done with mechanical thermostats.
Like the old dial on your wall at home.
Exactly. A bulb senses the temperature, and a switch physically clicks shut or open.
Simple, reliable.
Reliable until it isn't. They have moving parts, the contacts wear out, and they aren't very precise. If you need to keep a chemical at exactly 150 degrees, a mechanical thermostat might swing from 140 all the way to 160.
And in some chemical processes, that swing ruins the product.
It absolutely does. It's not just about not freezing, it's about the chemistry.
Right.
So the industry moved to solid-state electronic controls. No moving parts. They can switch on and off in milliseconds. This allows for what they call average current control. Instead of full on or full off, it pulses the power to maintain a dead steady temperature line.
The source material also highlights a specific feature of these electronic controllers called soft start. Why is this so critical? It sounds like a luxury feature, but the notes make it seem mandatory.
It's crucial, specifically for our favorite self-regulating cable.
Okay.
Remember how it works? It conducts more electricity when it's cold.
Right. The carbon particles are all squished together.
Well, imagine starting up a huge system on a minus 40-degree morning. The cable is freezing. Its resistance is practically zero. It's basically a short circuit.
So it's going to ask for a massive amount of power all at once.
A huge inrush current. If you just flip a standard switch, that surge looks like a fault to your distribution panel.
Yeah.
Pop, the breaker tripped.
Does it flip it back and pop again?
We call it nuisance tripping. You can't even get the system running.
So what does soft start do?
A soft start controller solves this. It doesn't hit the cable with full voltage instantly. It teases it. It slowly ramps up the voltage over a few seconds or minutes. As the voltage creeps up, the cable warms slightly, its resistance increases, and then it settles into a normal operating range without blowing the breaker.
It wakes the system up gently instead of dumping a bucket of ice water on it.
That's a perfect analogy. It manages the physics of the startup so the infrastructure can actually handle the load.
Let's shift gears to installation. Because reading through the field manual from the source text, I realized something. Pipes aren't just straight lines. They have valves, flanges, supports, bends, and apparently these are the enemies of heat trace.
We call them heat sinks.
Leak sinks.
Think about a metal pipe support bolted to a big concrete wall. That metal support acts like a radiator fin. It just sucks heat out of the pipe and dumps it into the cold wall.
If you just run the straight cable past that support, the pipe is going to freeze right there. Guarantee it. The heat loss at that support is way higher than the rest of the pipe. So the installation manual says you have to apply more cable at these points. You loop it, you double it back, you have to compensate for that heat loss.
It requires a lot of forethought. The section on valves was particularly specific.
Valves are tricky. A valve is a mechanical item. Eventually, it will leak or get stuck, and a maintenance crew will need to take it apart.
And if the electrician has wrapped the heating cable tight around the valve like a mummy.
The mechanic takes out a knife and just cuts the cable to get the valve off. Now you have a frozen pipe and a broken electrical system.
So what's the pro move?
You install it with a service loop. You leave enough slack in the cable so that the valve can be unwrapped and removed without disconnecting or cutting the main trace. It's about being considerate to the guy who has to fix the valve 5 years from now. Speaking of pro moves, I want to highlight one specific tip from the source about terminating that self-regulating cable. It's about the metal braid.
Oh, yes. This is the classic don't screw this up instruction. These cables have a metallic braid for protection and grounding. To connect the wires, you need to peel that braid back.
And the instinct is to just snip it off, right? Or cut it lengthwise like you're peeling a banana.
Right. But if you take a knife to that braid, you risk nicking the soft insulation underneath. If you nick it, you create a future short circuit.
So how do you do it without a knife?
You use physics again. You take a screwdriver and you poke it through the braid, opening up a little window. Then you bend the cable and fish the inner core out through that hole.
You pull the inside through the outside.
Exactly. It turns the braid into a neat little pigtail that you can use for your ground connection. And you haven't brought a sharp blade anywhere near the delicate core. It's a technique that separates the novices from the pros.
I love those kinds of details. It's so tactile. Now, we have to talk about safety. We are mixing high-voltage electricity with metal pipes, often carrying flammable liquids. Ground faults seem like a huge concern.
They are. But there's a really interesting nuance here compared to, say, residential safety.
Oh.
In your bathroom, you have a GFCI outlet. If it senses a tiny leakage of current, like 5 milliamps, it shuts off instantly to save your life.
But industrial trace heat leaks a little bit naturally, doesn't it?
It does, especially long runs of cable. They have what we call capacitive leakage. If you used a bathroom GFCI, it would be tripping constantly, the system would never run, so industrial standards are set higher, usually 30 milliamps.
But the source mentions an exception for critical processes that I found really interesting. It seems like a moment where two safety rules collide.
This is where engineering meets risk management. So imagine a chemical plant. You have a pipe carrying a volatile substance. If that pipe freezes, the pressure builds up and the pipe explodes, releasing a cloud of toxic gas.
That's a mass casualty event.
Right. Now imagine your heat trace system develops a small ground fault. If you have a standard breaker, it trips. The heat turns off, the pipe freezes, the pipe explodes.
So the safety device actually caused the disaster.
Exactly. In that specific scenario, the electrical fault is less dangerous than the process failure. So the electrical code allows for ground fault detection instead of interruption.
So the breaker doesn't trip.
No. Instead, a siren wails, a light flashes in the control room. It screams, "Hey, there's a ground fault here, fix it ASAP." But it keeps the heat on. It prioritizes the process safety over the electrical fault,
Wow.
assuming that qualified staff will rush over and manage the situation.
That's a fascinating trade-off. It's not just safety first, it's which safety is first.
It's a calculated risk, and it's pretty unique to heavy industry.
Finally, let's touch on troubleshooting. When something goes wrong in a system that's a mile long and covered in 3 inches of insulation, how do you even find the problem? You can't see the cable.
It's the invisible needle in the haystack. You need a megameter or a megger. It shoots high voltage into the cable to test if the insulation is holding up.
But if the test fails, if the megger says short circuit, where is it? Mile 1, mile 2, you can't strip all the insulation off.
That's the hunt. You use a divide and conquer strategy. You go to the physical halfway point of the circuit, you cut the power, disconnect the cable, and you test both directions.
And if the first half tests good, the problem has to be in the second half.
Exactly. You've just eliminated 50% of the pipe. Then you go to the middle of the bad half and you test again. You keep cutting the problem in half until you find it.
It's binary search for the real world.
It's logical, methodical detective work.
So looking back at all of this, we started with a simple frozen pipe, and we ended up with smart polymers, skin effect physics, and these incredible trade-offs in circuit breaker design.
It really highlights the hidden complexity of the world around us. We drive past refineries or see pipelines and we think of steel and oil. But really, there's this whole nervous system of electricity running alongside all of it.
Yeah.
Without these heat trace systems, modern industry in cold climates simply stops. The oil doesn't flow, the food processing plants freeze up, the safety valves jam.
It's the invisible veins keeping the industrial body warm.
That's a perfect way to put it.
I want to leave you with a thought about that self-regulating cable. We spend so much time today talking about AI, smart homes, digital tech. But here is a piece of plastic and carbon dust that effectively thinks. It makes decisions about energy usage just based on its physical properties. No code, no software, no vulnerabilities to hacking.
It is analog intelligence.
Exactly.
Yeah.
And it makes me wonder, what other complex problems in our world could be solved better by materials that think physically rather than just throwing a computer chip at them?
That is a very big question and one worth exploring.
Something to chew on. Thanks for listening to this deep dive on heat trace. Stay warm out there.